Okay. So J is at negative 4, 2. K was at 0, 3. L is at 1, negative 1. And M is at negative 3, negative 2. All right, what type of shape is it, is the question. So first we need to check if it's a parallelogram. And again, the way I kind of was recommending that we do this is by using the diagonals, not the sides. So check to see if the diagonals have the same midpoint. So find the midpoint of JL. That'd be negative 4 plus 1 over 2, and 2 plus negative 1, or 2 minus 1 over 2. So that would be negative 3 halves, 1 half. And then midpoint of KM, that'd be negative 3 plus 0 over 2. Negative 2 plus 1 over 2. So that'd be negative 3 halves. What? Oh, this one?
No, for K.
Okay. Oh, I'm sorry. I'm looking at JM. My bad. KM. Oh, there's the problem. Thank you. Okay. So negative 2 minus 3. There we go. So that's negative 1 half. That makes more sense. Thank you. That's the one I did? No, I did the wrong one. Undo. Undo. Magic undo. Okay. Negative 2 plus 3. Right there. There it is. I know it had to work out. There we go. Labeled the point wrong. There it is. So they do bisect each other. They have the same midpoint. Then I can check to see if they're perpendicular or not. So slope of JL. And now they have the right points. That should be easier. Y minus y, so 2 minus negative 1. Negative 4 minus 1. That's 3 over negative 5. Slope of MK, negative 2 minus 3 over negative 3 minus 0 is negative 5 over negative 3, which is positive 5/3. The slopes, these two are perpendicular. That means it's a rhombus, because the slopes are perpendicular. Finally, the length of JL. So x's are negative 4 and 1, so negative 4 minus 1 squared. Y's are 2 minus negative 1, so 2 minus negative 1 squared. So that's negative 5 squared, which is 25. 3 squared is 9, square root of 34. And MK, give myself a little more space. MK, negative 3 minus 0 squared. And JL, MK, I'm sorry, I'm doing MK. Negative 3 minus 0, 2 minus 3. Negative 2 minus 3. Squared. So that's negative 3 squared, which is 9. Negative 5 squared is 25, so that's square root of 34. They are congruent. So the diagonals bisect each other, they're parallel and congruent, that means it's a square. It's all three work. Yay. That proves to me it's a square. Now, if they weren't congruent, but they were just perpendicular, that would be a rhombus. If they weren't perpendicular, but they were congruent, it would be a rectangle. If they were neither, but they'd still bisected each other, it'd just be a plain old parallelogram. So once you find they bisect each other, then you have to perform both of these other tests to see what's going on. Actually, you'll have to perform all the tests pretty much anyway. Yes. Sure. They're from different pictures. It's kind of a bummer. Well, you had to use trig to get 36. Okay. So for 36, we had a rhombus. So okay, we had a rhombus. 53 and 8 were the measurements were given. And this is 8. And it wants us to find, for 36AE, which is this section right here, X. Okay? That's what it wants us to find. So the diagonals bisect each other. The diagonals bisect the angle, so this angle is also 53 degrees. And this is a right triangle, so we have a right triangle inside of our rhombus that has an angle of 53. This side is X, or this side is 8, excuse me, and this is X right here. And the only way we have solving that is by using trig. So remember last chapter when we were doing the trig, I said, you know, it's going to come back. We're going to still use it. This is an example of where. The only way we can solve that is with trig. So if this is my angle, 8 is which side? Opposite. And X is adjacent. So it would be what function? Tangent of 53 is opposite over adjacent, so X equals 8 divided by tan 53. And that's going to be about 6. 6.03. Very close to 6. So yeah, that's, I mean, definitely that would probably be more of an extension style problem on a test or quiz. Pop that out. Thank you. But yeah, that's not outside the realm of our possibilities of types of questions we're going to see. That we're going to have to use special triangles or Pythagorean theorem or trig. Since we've passed that unit, that's all fair game now in any problem. You can't just forget it. It's going to come back. It'll definitely come back again when we get to chapter 11, I think it is, which is not that far away. It's April. We'll get to that. We'll definitely be using it quite a bit. So that was trickier. Number 38, that was just triangle sum. So it has to be 56 degrees. The diagonals intersect given that PTS is 34 and QS is 10. Yeah, because that has to be a right angle. Because that angle has to add up to 90. PTQ has to add up to 90. So 56 plus 34 is 90. That's why that came off. Others. Today we got another big load of stuff to talk about. Sorry. And that's trapezoids and kites. These are our last two new shapes, so this is pretty much it for the new stuff. For this entire unit, actually. This is pretty much it. But yesterday we talked about all these things that are parallelograms. All these quadrilaterals are parallelograms. Rectangles are parallelogram, rhombuses are parallelograms, squares are parallelograms. They're all parallelograms. But now we need to talk about things that are not parallelograms. Okay? Trapezoids and kites are quadrilaterals that are not parallelograms. So all these properties of parallelograms you've been working with don't apply. Their diagonals do not bisect each other. Both pairs of opposite sides are not parallel. They do have some properties in common, but nothing that would make them a parallelogram. So let's take a look at their definitions. Trapezoids have exactly one pair of opposite sides. The second pair of sides are not parallel. Only one pair of sides is parallel in a trapezoid. Kites have two pairs of consecutive congruent sides instead of opposite congruent sides. And that's pretty easy. I mean, think about a kite. You got the two shorter sides, you got the two longer ones, right? Just picture a kite. That's why we call them kites. So trapezoids and kites are not parallelograms. Now, parts of a trapezoid. We're going to refer to this a lot, so get used to it. A trapezoid, essentially, think of it like a triangle that we then spread out and make a third side. Okay, we've got the two legs, I've got the base, but I've got a second base. The parallel sides are both referred to as bases, base 1 and base 2. So we've got two bases, the parallel sides of the bases. The bases could be on the top or the bottom, and I could rotate this trapezoid. This isn't going to be pretty because the words didn't rotate with it. But the two parallel sides are still the bases. Okay? Base has nothing to do with bottom. Each base has two angles associated with it. These are the angles for base 1. These are the two angles up here. Okay? Those would be the two angles for base 2. And like I say, the non-parallel sides are referred to as legs. So we had legs in right triangles before. We had legs in isosceles triangles. Now we have legs in trapezoids. Same word, slightly different use. In general, trapezoids are not very interesting. Sad to say. They have one pair of parallel sides, and that's pretty much all we can say about them. What is interesting is when a trapezoid becomes isosceles. So, I mean, one of the things we can look at now in the coordinate plane, if I test and I see the diagonals don't bisect each other, now it's not a parallelogram. We do have to now check to see, well, is it a trapezoid? Do I have any parallel sides? Now we got to start measuring the slopes of all the sides. So now we might have to start doing more measurements in our coordinate plane again. Like I said, though, what is interesting is when the trapezoid is isosceles, which means the legs are congruent. That's when things start happening. Because when these legs are congruent, it means that these base angles to the same base are congruent. And these two base angles have to be congruent when those legs are congruent. Not always. Not only that, but when it's an isosceles trapezoid, the diagonals are congruent. So, interesting things happen more with isosceles trapezoids. Now, one thing that is true with any trapezoid, before we get too far along, another thing that's true about a trapezoid, I'm going to draw it so it's definitely not isosceles. Okay? These two sides are parallel. That's not an isosceles trapezoid. That's just a plain old trapezoid. But one thing that's true about any trapezoid is if I take two angles like this, call this angle 1 and this angle 2 down here, what has to be true about angle 1 and angle 2? Those two have to be supplementary, don't they? Because if I expand my picture to be parallel lines in a transversal, those are consecutive interior angles, aren't they? So right back to our parallel lines theorems. And the same with angle 3 and angle 4 here. They have to be supplementary. However, there's no necessary relationship between 1 and 3 or 2 and 4 unless the trapezoid is isosceles. And the opposite angles are not congruent. The opposite angles are not supplementary. Nothing going on there. Again, until it becomes isosceles, and then things start happening. So we do get some supplementary angles in a trapezoid, regular old trapezoid, but not a lot. And they have to be very specific pairs. They have to be pairs along the same leg. They're supplementary. But these base angles will only become congruent if it's an isosceles trapezoid, and again, opposite angles, not necessarily anything, unless it's isosceles. The mid-segment of a trapezoid is the segment that connects the midpoints of the legs. The mid-segment is parallel to the sides, splits it in two. It's like the mid-segment of a triangle, of an isosceles triangle, or any triangle for that matter. And the length of the mid-segment is half the sum of the bases, or it's the average of the bases. Lots of stuff here. The length of the mid-segment is the average length of the bases. We add and divide by 2. Now, in a lot of cases, that's pretty easy. And like I say, the other thing is it's parallel. So you get all sorts of pairs of interior angles and sorts of things going on here. Now, sometimes that's pretty easy. Let's look at this one to start with. If this is 6 and this is 10, what's this going to be? 8. 6 plus 10 divided by 2, or 8. And you'll also notice there's a pattern here, plus 2, right? Now, I could use formulas here. I could just figure this out. Gosh, from 7 to 5 is a decrease of how much? 2. So better be the same here because it's in the middle. So how long's B going to be? 3. So we just have plain numbers. Mid-segments are pretty easy to work with. With algebra, it can get a little trickier. Tell you, we'll have to set up equations. Now I know that 9 is the average of these two lengths, but I don't know what they are. So we have to set up our equation. And this is a little trickier than what we've had to do in the past. So you have to use our formula now. It's this plus this divided by 2 equals that. So I have to do 2x plus 1 plus x minus 3 divided by 2 equals 9. We haven't had to do a lot of equations that are that complex. Pretty much most of our equations this year have been set them equal to each other or add them up and set them equal to 180. This is different. Now I've got a formula. Base 1 plus base 2 divided by 2 is the midsegment. And to solve this, we have to use our algebra skills a little bit. First, multiply both sides by 2. That cancels out the division. That gets rid of the fractions. So 3x minus 2 is 18. And now we're good. Probably wasn't going to guess 20/3 for an answer. But that's the value of x in this case. 20/3 or 6 2/3. So a little different. Now, when the variable's on the mid-segment, it's actually a little easier. In fact, it's a lot easier. Here's what we do in the variables in the mid-segment, but we know these two lengths. I ignore that for a minute, completely. Just cover that up. And I say, gosh, if this is 16 and this is 22, what's that middle segment going to have to be? Well, 22 plus, or 16 plus 22 is what? 38 divided by 2 would be 38 divided by 2. 19, thank you. Somebody. That segment must be 19, right? Plus 3 plus 3, right? Oh, well, that means 2n minus 1 equals 19. There's my equation. I don't have to set up a big formula for that one, do I? This one I had to set up the big formula for because base 1 plus base 2 divided by 2 equals the mid-segment. This one is actually easier because I know both the bases. And I can solve that mid-segment pretty easy. So we can really change the difficulty level of these problems very quickly by going from just plain numbers, really simple, to variable expressions. Can be more complex, but if we're smart and think ahead, if I have plain numbers for 2 of the sides, I can solve the third one pretty easy. It gets tough when I have variables for 2 of the 3 measurements, or even more tough when I have variables for all 3. Then it really gets interesting. Solving trapezoids, we're going to get a lot of problems like this, just solve things out with trapezoids. So we can start figuring things out. Let's start by finding our angles. It's an isosceles trapezoid, so angle A is going to have to be 75. Angle C is going to have to be 95, because these two have to add up to 180. And angle B is also going to have to be 95. All right. Find the length of this side right here. Again, we're getting into an extension type problem here where we're going to have to get kind of careful about things. But you want to know what? If this is 12 and this is 18 and it's isosceles, I could draw these two altitudes in and make what kind of shape inside of my trapezoid? A rectangle. And so if this is 12 and this whole side is 18, this piece has got to be 12 here, leaving me how much on each end? 3 on each end, right? 6 total. 6 total, but since this isosceles is split evenly. And what do I have here now? I have myself a right triangle. X is there. 75 degrees is here. Right angles here. And this side we know is 3. Gosh. Adjacent hypotenuse. Cosine of 75 is 3 over x. So x equals 3 divided by cosine of 75. And we're right back to our trig, aren't we? Again, that is a more advanced extension level problem. But this is the type of thing that we're able to do with trig. This is why we learned trig in the last chapter, because it is a very powerful tool. It allows us to solve things that up to now we'd have had no opportunity to solve. I'd have never been able to find the length of that side without trig. It's the only way we can do it. So trig gives us power. By the way, in case you're wondering, 3 divided by cos 75 is about 11.6. So finding A, B, and C, not bad. Finding X, challenging. but not undoable if you remember your trick. Let's look at the kite. The kite is not a parallelogram, but it does have two pairs of congruent sides. The difference is the congruent sides are consecutive instead of opposite. Classic kite shape. The kite does have one pair of congruent angles. That's this whole angle and this whole angle. Those two are congruent. These two are not. If it had two pairs of congruent angles, it would be a trapezoid or a parallelogram, right? Two pairs of opposite congruent angles would make it a parallelogram, so it only has one. The diagonals do not bisect each other, but in a kite, the diagonals are perpendicular, meaning we have right triangles again, which means Pythagorean theorem, and all our right triangle stuff from last chapter is back in play. Again. So kites, one pair of congruent angles, two pairs of consecutive congruent sides, one pair of congruent angles, diagonals are perpendicular. Those are the properties for my kites. Again, if I wind up in the coordinate plane, how do I show something's a kite? Well, first we'd have to start measuring sides, measuring diagonals, measuring all sorts of things. In fact, we'd probably have to check first to see if the diagonals bisect each other. They don't. And then we'd probably go and try to measure the four sides using distance formula to show two pairs of consecutive congruent sides. So four distance formulas. This is one of the reasons why we always want to sketch a graph on graph paper of what we're doing before I start doing the measurements, because the picture is going to kind of tell me what I'm looking for. And when I looked at that first one we did today, I was thinking square the whole way when I looked at that picture. I saw those four dots and how that drawing, that looked like a square to me. So I'm thinking, what do I need to do to show it's a square? If I had a picture come up looking like this, I'm not thinking parallelogram, I'm thinking kite right away. So maybe I'm just going to measure the lengths of all four sides right away. Oh, look at that. Two congruent pairs, but they're consecutive sides. I've already proven it's a kite. Couldn't be a parallelogram, it must be a kite. So as long as we're sketching first, we're usually okay. Find the perimeter of the kite. Problem with the perimeter of the kite here is we don't know any of the sides, do we? But I do know that these are right triangles. So a Pythagorean theorem is in play. And fortunately, these two triangles are congruent and these two triangles are congruent, so I only have to do Pythagorean theorem twice. So x, 5 squared, plus 8 squared equals x squared. And over here, 5 squared plus 12 squared equals y squared. 5, 12, what is my Pythagorean triple? 13. Okay, so that one's an easy one because the Pythagorean triple. 5, 8 is not a Pythagorean triple, so 25 plus 64, 84, 89 is x squared. So x is the square root of 89, which doesn't simplify. So the perimeter of this would be 13 and 13, which is 26, plus 2 root 89, because there are 2 root 89s, whatever the units are. U for units. All right? So there's my perimeter. Exactly. Again, using the right angles, using right triangles, using the Pythagorean theorem. Didn't need trig there, just the Pythagorean theorem was enough. There's a lot of stuff in this section. I mean, you've been getting tons of information the last couple days. It's a lot to take in. What kind of shape is this going to be? Based on the information we have here, what kind of a shape is this? Rectangle, rhombus, square, parallelogram, kite, trapezoid? Just regular old quadrilateral to the above. Which one is it? What do you say? Okay. Jared, what do you say? Kite. Why? Why do you say kite? Because it looks like a kite? Not judge based on appearances necessarily. What facts do we have to tell us it's a kite? Yeah, these two sides are congruent and they're next to each other. These two sides are congruent and they're next to each other. Oh, okay, that's the definition of kite. That's what it means. All right, so, what are properties of kite? Well, I'm told this angle here is 60 degrees, and this is a right angle down here. What's angle Y going to have to be? 60, because those opposite angles like that, because they connect the non-congruent sides, those two are congruent. So I've got 60, 60, and 90 used. Is this going to be 90? No. It couldn't be. Because if that angle was 90, then that shape would be a trapezoid, wouldn't it? Because both pairs of opposite angles congruent make it a trapezoid. Trapezoid. Parallelogram. Who agreed with me when I said trapezoid? Shame on you. Shame on me for saying trapezoid. Okay? It'd be a parallelogram because both pairs of opposite angles would be congruent. So how many degrees are there totally going to be in any quadrilateral? 360. So that leaves me 300, 210, 150. Okay? So lots of interesting things happening with kites. Just a real quick review. In a rectangle, WXYZ is the following always, sometimes, or never true. Angle WXZ congruent to angle YXZ. Now, how in the world do we answer this picture? I don't know what it looks like. What are we going to do? Draw a picture. It's a rectangle. Gosh, it's a rectangle. It's called WXYZ. I want WXZ. Oh, that'd be this angle. Congruent to YXZ. Okay, that's angle 2. So we got angle 1 and angle 2. And angle 1 and angle 2 always, sometimes, are never going to be congruent. Ooh, I've heard all three answers. Let's think about it. Right now, with this triangle drawn, or rectangle drawn as it is are they going to be congruent? No, because the diagonals do not bisect angles in rectangles. They do in rhombuses, not in rectangles. So it's not always, is it? Is it never? Is there any type of rectangle we could have where they are congruent? What would that rectangle look like? A square. It'd be also a rhombus, wouldn't it? So it could be congruent if it was a square. So my answer is sometimes. Sometimes, yes. In rhombus ABCD, the diagonals intersect at point E. Given the measure angle BAC is 53 and DE is 8, find the measurement angle DAC. Again, just a written description. So what we're going to have to do, we're going to have to draw a picture. And today we are out pretty quickly here. So actually, this is from your homework last night. We won't get into that right now. Let me put tonight's assignment on the board. We're running out of time. So good news is I don't think there's any vocab tonight. All right. Here we go. Yep. So you will need some graph paper. Make sure you grab some on the way out. It's 546, 3 through 20, and 25 through 27. There's no vocab. And basically we've learned everything we need. The new section tomorrow essentially is a review section. So we're diving right into the review already. Remember that we only meet for a brief time on Thursday for additional review. And then our next quiz is already on Friday. Yes. They haven't given us lists of people yet. We've been given our room assignments, but I don't know, and I know I've got 10th graders, but I don't know who. All morning. So it's state mandated, so everyone has to take it. Oh, we got classes in the afternoon, so you want to be here. All right. So anyway, about 3 seconds. So there's your assignment, 3 through 20, 25 through 27, 546.